Hi, I'm Emma, and welcome to my channel. Chances are you're watching this video because someone said you should use PID to control something, maybe a motor or a robot. I mean, no one wakes up in the morning and says to themselves, you know what I need? A PID controller. And then maybe you started searching around on the internet and found some stuff about a plant or process variables that was accompanied by some pretty advanced looking math equations. Well, don't worry, it's not as complicated as it might seem. All we need to do is break it down into simpler concepts. Let's get to it. Before we get started, shout out to BuilderDude35 for teaching me about proportional line followers when I was Tiny Emma building Lego robots. He laid the foundations for what I'm about to teach you. First things first, what exactly is a PID controller and what would you need one for? Well, at its core, it's a mathematical approach, typically used in software, to make adjustments in order to keep a machine like a robot doing what it's supposed to be doing. Some common places where you might find PID controllers are cars, robots, drones, or factory machinery. In a car, for example, the driver of a car usually makes all sorts of adjustments to keep the car on the road. But if you wanted the car to do things on its own without a human involved, we need a way for the system to make these same adjustments by itself. That's where a PID controller helps out. And in many cases, it can make adjustments faster than a human can. Let's talk about the ingredients we need for a PID controller. First, we need some sort of mechanism or system that needs to be controlled in some way. Most of the time, the actual thing you'll be controlling will be a motor. For the purposes of this channel, I'm just going to use the word robot instead of mechanism, but just know that you can use these concepts for a lot more than just robots. Second, we need some sort of processor that we can program. In the first robotics world, this would be an FLL Spike Prime hub, or an FTC control hub, or an FRC Robo Rio. For your own projects, this might be an Arduino or a Raspberry Pi. Third, we need a goal that you want the robot to achieve. We'll get into some examples of these in just a moment. We'll call this the set point, and you can think of it as where you want to go. And lastly, we need a way to measure where the robot is in relation to its goal. You can mentally label this as where you are. This part is really important because how can you adjust what you're doing if you don't know whether you're on track or not? Okay, let's talk about goals or set points a little more now. What kind of goals can you set? Well, there's really two main categories: position and velocity. For position, this covers things like distance along the ground, such as a particular distance you want to drive, or maybe a line you want to follow. But position can also be angular, like the angle of a wheel or an arm. The important thing to notice about position goals is that you tend to stop when you get there. Or, in other words, if you're using a motor to turn your wheels to get to a specific position, you might shut off the motor when you arrive. Compare this to something like velocity, where you don't want to shut the motor off, you want to maintain the speed. Here's some common examples of where you might want to control velocity: the cruise control in a car, the speed of the wheels on a ball launcher, or the propeller speed of a drone. Naturally, we'll want to represent both the set point and measurement as separate numbers. It's really important that these two numbers have the same units. That means if your goal is to drive 30 centimeters forward, your set point should be 30 centimeters, and your measurements should also be in centimeters. Mixing centimeters and encoder ticks, for example, isn't going to work. Likewise, if you want to turn a wheel to 45 degrees, you wouldn't want your set point in degrees and your measurement in radians, so make sure you convert them when needed. Once you've got both a set point and a current measurement, you can then find the difference between them by subtracting the measurement from the set point. In the world of PID, we call this difference the error. For programmers like me, it can be a little confusing because errors usually represent a mistake. But in this context, error represents how far off the mark we are, like shooting an arrow at a bullseye. Once we know how far off the mark we are, we can then use that information to make an adjustment. There are 3 different parts to a PID adjustment. You may already have guessed that these parts are labeled P, I, and D. Okay, I'm going to show you the mathematical formula behind every PID control. Boom! There it is in all of its mathy glory. It can look intimidating, especially because there might be some symbols in there that you haven't learned in school yet. The good news is that you don't really need to completely understand all of the math to understand how it works. The concepts are not as complicated as they look when written like this in math notation. What you'll end up writing in code is a simplified version. But this form serves as a starting point to explore a few of the features. The first thing I want you to notice is that there are 3 sections joined by plus signs. The next thing to notice is that there are 3 uppercase Ks. And hey, look at that! The subscripts are P, I, and D. In this math notation, the letter K stands for a constant, or a number that doesn't change. Why they picked K, I have no idea, but I guess C was already taken. Let's get rid of the Ks and just use the letters. Each section has this pattern, a constant multiplied by a value. We'll ignore the value to the right of the constant for now. I'll explain where these come from in a moment, but I want to focus on the constants for now. For most of us, this is how we interact with a PID controller in a robot. There's usually a ready-made class or function that calculates the values on the right, but it's up to you to figure out what the constants need to be. There's a couple of words that describe the purpose these constants serve, like coefficient or factor, but the one that I like is the word gain because it leads to a nice analogy. If you've ever looked at a sound mixing board, there's typically a knob labeled gain on each of the channels. If you turn the gain all the way down to 0, you generally won't hear any sound. The more you turn up the gain, the more the sound is amplified. In a PID controller, the signals coming into the P, I, and D sections are multiplied by the gains and then added together, similar to channels on a mixing board. You, as the robot DJ, have to decide how much of each to add to your mix to get the right output. You do this by increasing or decreasing the gain to add more or less. If you were to set P, I, and D all to 0, the output of your PID controller would be 0. Okay, now that we've got some knobs to turn, let's find out what they do. The gain labeled P stands for proportional. This means that it reacts in a proportional way to the error. Or, in simple terms, big error means big change, small error means small change. This might seem pretty obvious to you, but not all systems can react in a proportional way. Take the thermostat in your house, for example. A lot of furnaces are either off or on, so if it's too cold in your house, the thermostat turns the furnace on. It doesn't matter whether your house is 1 degree too cold or 10 degrees too cold. The thermostat turns the furnace off once the temperature reaches the set point. This type of control, where the system turns on and off, full blast each time, is called bang-bang control, because bang, it's on, bang, it's off. If you've ever been in First LEGO League, the line followers that most kids learn to code uses this kind of bang-bang control. You'll notice it because the robot always turns a fixed distance, so it ends up zigzagging back and forth over the line. But we can be more precise than that. Let's use a very common example in robotics. You want your robot to drive a very specific distance. For our made-up example, let's use 30 centimeters. This will be our set point. But remember, we need a second number. We need a measurement of where we are. The most common way that we can know how far the robot has driven is to use a motor encoder. I won't go too deep into how an encoder works because that's a topic for a different video, but the short explanation is that an encoder counts how many times the wheel goes around, and we can use the circumference of the wheel to know how far it traveled. The distance our robot has traveled is our measurement. As the robot is running, the code checks these values over and over in a loop. Imagine a bunch of kids in the back seat yelling, "Are we there yet?" over and over. Dad sighs, looks ahead of the road and says, "No kids, we're 30 centimeters away yet." Now, If you were using bang-bang control, you might turn on the drive motors to 100% speed, and the robot would start traveling forward. You continuously check the distance you've traveled, and the moment it hits 30 centimeters, you stop the motors. What would happen? Well, unless your robot is super tiny, it's not going to stop exactly at 30 centimeters. The weight and momentum of your robot will make it keep rolling past the mark. Ideally, we want to start slowing down before we get to the set point. The motor should start out full speed when you are far away, and then drop down to 0 by the time we get to the set point. Hey, remember that error number? Let's look at what happens to it as the robot drives. At the start, when the robot hasn't moved yet, the measurement is 0, and the set point is 30. 30 minus 0 is 30. How about after the robot has traveled 20 centimeters? Now the error is just 10, or 30 minus 20. And finally, after the robot has traveled 30 centimeters, the error is 0, because where we are and where we want to be are finally the same spot. This number seems to ramp down nicely, but we can't really use it directly because it goes from 30 down to 0, and our motor speed is probably either a percentage or a voltage. I'm going to pause for a moment and pay special attention to this problem because it's a pretty common beginner mistake. The units on your set point, measurement, and error values will almost always be different from the range of numbers that the motor or other movement device needs for input. In our example, our error value is in centimeters, but our motor needs to know what speed to run at as a percentage from -1 to 1. For other systems, the motor input might be a voltage, like -12 volts to +12 volts. So you'll need to make sure that the value your PID controller spits out is something that your motor can understand. If we were to set the P constant to 1, then when our error is 30 centimeters, 30 times 1 is 30. If we were to feed the output of the PID calculation to the motor, then it would run full speed until 1 centimeter before the goal, where it finally drops below 1. Well, it's possible to do the PID calculation and then later convert the output for the motors. Most people adjust their gains so that the resulting number is in the right range. In our example, if we set the P constant to 0.2, this would mean that the output would start dropping below 1 at about 5 centimeters away. If this is a big, heavy robot, then it might need to start slowing down earlier, but it might be just right for an FTC robot. You'll have to tune the numbers for what works with your robot. Overall, the proportional gain acts like a spring. The further away from the set point it is, the more effort it applies to get there. One of the decisions that you'll need to make is how quickly do you want your robot to get to the goal? What if, instead of 0.2, you choose 0.02? At 30 centimeters away, your robot already would only be going about 60% speed. So it'll eventually get to the goal. It'll just take a lot more time. In many situations, the proportional parameter might be the only one you need, and you can just leave the other two at 0. In LEGO League, I could get pretty smooth results with just a proportional line follower. However, as you build faster and heavier robots, and you want them to respond quickly, there is a common problem that you may encounter with the proportional gain. The momentum that the robot picks up as it moves may cause it to overshoot the goal. At that point, the proportional response will try and pull it back to the goal, and it may overshoot again. It may go through several oscillations as it tries to get to the goal. In many situations, it's really important to not overshoot the goal. Think about what could happen if the machine you're controlling is a car and the goal is a stop sign. If you roll past your goal, you could roll into traffic and get hit. So we have this problem. We generally want to get to our goal as fast as possible. So that means turning up the P gain as high as we can get away with. But this comes with the risk that we'll overshoot the target. We need a way to check how fast we're speeding towards the goal and start hitting the brakes when we see the goal approaching. This is where the derivative gain can help us out. I'll explain where the name derivative comes from in just a moment. But for now, just know that it's a calculation that shows how fast we're coming up on the set point. In order to calculate this, we have to keep track of what the error was during our last trip through the loop. This is pretty easy to do in most programming languages. Just create a variable like previous error and then store our current error in there as one of the last things we do in our loop. The other thing we need is the amount of time that has passed since the last loop. In many systems, you may already know what this is. In FRC, for example, the loop runs every 20 milliseconds. If you don't know what it is, you can always calculate it by keeping track of the time of the last loop and subtracting it from the current time. To visualize this, you can plot the two sets of values on a graph, with time on the horizontal axis and error on the vertical. If you draw a line from the old value to the new value, you'll see that the line has a slope. The steeper the slope, the faster the error is changing. If you divide the difference in the two errors by the difference in time, you get a number that represents this slope. In calculus, when you find the slope of a line that's drawn tangent to your function's graph, it's called a derivative. That's where the name of this gain comes from. But you don't have to know much more than how to figure out the slope of a straight line. Just like the P gain, you can mix in more or less of the D gain, but unlike the spring, the D gain works to slow things down, a bit like wading through a pool of water. Slow movements are mostly unaffected, but the more drastic movements you try to make, the more it pushes back. Now, you might be wondering why I skipped over I. Well, even though PID is the order that most people say it, I would recommend tuning it in this order. The overall advice for tuning a PID controller is to start with everything at 0 and then start turning the P up just until it starts to oscillate, and then mix in D until it stops oscillating. But what about the I gain? Well, many times you won't need it, but it's very handy to solve a specific problem. Sometimes, no matter how much you fiddle with the P and D constants, you just can't get it to reach the goal. There may be an outside force acting on the robot, like friction or drag. We call this situation steady-state error. Or consider an arm that sticks out horizontally from the robot. As it pivots, the motor will have to work harder to overcome gravity. If you think of P as reacting to the current error, and D as reacting to the future error, well, that leaves I reacting to the past error. To visualize how this works, let's plot two things on a graph. First, here's the set point. To make things simple, we'll keep the set point the same for the entire time. So that makes it a horizontal line. Second, we'll plot a hypothetical graph of a measured value that gets close but can't quite reach the set point. If we pick any moment in time and draw a vertical line, it will intersect both lines. The error is represented by the line segment in the middle. But in reality, the loop typically runs every few milliseconds, so let's expand that line to a rectangle that is as wide as the loop time. You can find the area of this rectangle by multiplying the height by the width. Cool, now what do we do with this? Well, imagine we take all of these rectangles and add them all up. What we now have is a number that represents how far off we've been in the past. Obviously, it can get pretty large, but if we only turn the I knob just a little bit, when the error piles up, it'll serve to nudge the robot enough to get rid of the steady-state error. Again, in calculus, this process of summing up the area under the curve is called an integral, which is what the I stands for. So, to recap, P means if you're not where you want to be, get there. I means if you haven't been where you want to be for a long time, get there faster. And D means if you're getting close to where you want to be, slow down. If you'd like to play around with a PID simulation and see how to tune these gains, click the link in the description. Happy PID tuning!